and then I'll get started. So what else have I planned for today's workshop? So in addition to talking about the theory and that in addition to talking about some of the challenges and like how you would do the aerodynamic simulations, I've also planned like a practical session. So what I did is I was able to find a model of a F1 car wing on GrabCAD. So I basically bought it and basically set up a very simple aerodynamic simulation on it so that you can basically learn from it, and in terms of settings, what are the settings that I used and why I did certain things, right? And the nice thing about this practical workshop is, I'm basically familiar with a particular CFD tool. You might be using a different tool, right? So like Star CCM or ANSYS Fluent. So whatever you learn in today's workshop can be directly applied there. So that is the outcome that is desired, and hopefully, we'll basically be able to provide that. So content, why run aerodynamic simulations on F1 cars? I think, again, that's a very basic question. Most of you will be able to answer it, but we'll just talk about it a little bit. And then we'll directly jump into today's main topic, like steps in performing aerodynamic simulations. And when I say steps, this is going to be the exact steps that you need to follow. There will be some recommendations based upon your models. Now, if you are currently a student who's running aerodynamic simulations, if you have a particular question in mind, this would be a great place for you to ask those questions so that I can give you customized answers. Then we will talk about how to understand results, right? So one of the confusions that many students have is that do aerodynamics is they basically get some colorful images, they plot streamlines, and they see really beautiful flow structures, but they do not know if those results make sense or not. How do you know if those results are correct or not? Then we'll talk about how much computing power you need, and then we'll finally talk about how to test new designs. I think this is where, again, people are struggling, and we'll definitely be able to provide some advice. Jennifer, thank you. All right. For those of you who are not familiar with F1 cars, right, I'm pretty sure everyone is, but here's some basic terminologies. So pretty much every component here, especially the wings, the front and the rear wings, the barge boards, the mirrors, and the complete bodywork is designed for aerodynamic performance, and not just aerodynamic performance. Okay, so let me start with a very simple question. Now, for those of you who are like really passionate followers of F1, who really enjoy the sport, right, know that all the components are designed, every little surface area has been designed carefully. So can anyone tell me what are some of the things, like for example, based on these parts, can anyone tell me why or for what some of these components have been designed, like, and how they affect the aerodynamic performance based on your knowledge of F1 cars? So for example, let's just take the front wing. What is the front wing or what is the rear wing designed for? That is the question that I'm asking, right? So similarly, you can think of any component here and you can basically explain it. This would be a great way to share knowledge as well, right? So the front wing is basically used to generate downforce. Yes, that's correct. What else is it used for? There is another reason for using the front wing, and especially with the end plate on it, there is a particular reason why the end plate is on there. Why? It helps in pushing the air upwards to increase the downforce. So Parth, that's exactly the same answer as Jennifer. So what other reasons? Like especially the end plate. What else can I use it for? Vortex. Yes. What's the advantage of having in vortex? Sunil and Divyam. Jennifer, exactly. It's the Y250 vortex. Jennifer, you can just reply publicly so that other people can also see what you're typing. So Jennifer, can you explain what the Y250 vortex is? Or does anyone know? If you don't know what the Y250 vortex is, you can just say no. You can just say no in the chat box. That's fine. Okay. So Jennifer, if you don't mind, can you explain what Y250 vortex is? Exactly. So yes, that's definitely one advantage of it. Okay, but we'll just wait for Jennifer to answer. We'll just give her some time to. Jennifer, are you typing in an answer? If you're typing in a response, you can just thumbs up. Your webcam is on. So okay. Anyway, I'll let you type it, but basically, see, when you create a vortex, right, you are not only channeling the flow, you are also creating suction effects near the mid portion of the car. Now, one of the ideal or basically one of the primary objectives of any aerodynamic design is at the end of the day, you need to basically slip through the incoming air as efficiently as possible. And one of the ways you can actually do this is by creating local depressions and pressure so that the air is pulled and you can efficiently move the air from the starting of the car and towards the end of the car. I don't have an animation or I don't have an image that shows the Y250 vortex and sorry, Y240 vortex, but if you basically go to YouTube, I'm pretty sure you'll be able to see it, right? So especially with F1 cars, pretty much any component that you think of is basically used for hair handling, right? Handling it correctly. In addition to this, there are also cooling requirements, right? So you have a very big engine sitting in your F1 car, which needs to be cooled, right? So air needs to be sufficiently provided through the air intake so that the cooling is also achieved. All right. So the reason why I'm kind of asking you to read up on terminologies is, especially if you're interested in F1 and if you're reading some kind of a paper or if you want to do a project, it makes sense to understand what is it that you're trying to simulate. And it makes sense to understand where that particular component is located in. If not, things are not going to be clear for you. And especially things like Y240, any F1 enthusiast knows that. Even though they are not an engineer, that is something that they know. Since many, sorry, Y250, thanks for correcting. Since many people are not aware of that, I feel like maybe you guys are not as much as a enthusiast, F1 enthusiast as Jennifer. So Jennifer is one of our students, just a disclaimer, and she's really passionate about aerodynamics. So that's why I know that she would know the answer for this question. Anyway, it doesn't matter if you know it, because the more important thing that we want to talk about in today's workshop is steps that are involved in performing these aerodynamic simulations. Now, these are the steps that you need at the end of the day. If you can do each of these steps correctly, you can simulate the aerodynamics and you can predict the aerodynamic quantities, not just on your F1 car. It could be a truck, it could be a passenger car, it could even be a building, doesn't matter. The concepts are always the same. So the first step is to create something called as the virtual wind tunnel, right? Does anyone know what the virtual wind tunnel is? Can anyone guess what virtual wind tunnel means? Again, guys, if the workshop is not interactive, I mean, if you guys are not interactive, then it's going to be very, very boring. So try to answer. If you do not know the answer, you can at least say no. That way I get some feedback so that I can simplify the question. What's a virtual wind tunnel? Can anyone answer? Okay, so it looks like we have a few answers. Wind tunnel using CFD software. Yes, that is the right answer. Aditya, no, that's fine. Don't worry about it. Computational domain, exactly. Sohan, access the aerodynamic performance of a model. Not really. So Jennifer and Anirudh, you guys are right. So when you take experimental setups, right? How do they determine the aerodynamic performance of your car? What they do is they take your car and they put it inside this really large room, and on one end of the room, there's a fan that basically blows air at a particular condition. This is what you call as a wind tunnel. And what you can do is you can set up force sensors or pressure sensors on the car, and you can basically estimate the amount of force that's acting on the car. In other words, the amount of force that's actually preventing the car from moving forward. This force would be the drag force. Similarly, if you throw a wing, and the same pressure forces or the same pressure sensors can be used to determine the lift forces and also the down forces, right? So this is what you call as a wind tunnel. And you might have all, if you are an undergraduate student, you would have definitely had at least one lab where you basically did something with the wind tunnel, correct? A virtual wind tunnel is nothing but the same concept, but done using a computer. That's why the keyword virtual is there in front of it, right? So it doesn't matter which software you're using, this is exactly the step. You first create a virtual wind tunnel, which at the end of the day is just a cuboid. You create a huge box, and inside this box, you basically import your vehicle's CAD model. Now, what are the components that you need to include? What are some of the approximations that you include in the model? That is a whole different thing. But let us just say that we have our car here. I'm just going to draw the circle which represents the car. It could be the F1 car, or it could be a passenger car. And then you assign something called as the boundary conditions. So what are those boundary conditions? Well, you can say that what is the pressure at this particular phase, or you can basically say what's the velocity at this phase, doesn't matter, or the mass flow rate. And then at the outlet, you basically specify the outflow pressure, right? The static pressure at the outflow. And then basically what the CFD solver is going to do is it's going to solve the CFD equations. And when you solve CFD equations, computational fluid dynamic equations, you can get the velocity, pressure, and temperature at each and every point that you specify in your computational domain. The points that you specify, right? That is what you call as your computational mesh. All right. This is something that you would create before you run the CFD simulation using a meshing software. So wherever the mesh exists, that is where you calculate the pressure and temperature, pressure, temperature, velocity. Then you can take these pressure quantities and you can just integrate it on top of the body that you're simulating flow over, and you will be able to calculate the lift coefficient or the drag coefficient. That's basically it. This right here is exactly the steps that you need to follow to perform aerodynamic simulations. So then obviously the question is, well, this seems very simple, then I should be able to do it very easily, right? Well, there are some challenges, and we'll be talking about some challenges in the next upcoming slides. And the way we are going to discuss these challenges is by trying to answer some fundamental questions. So first, let us say we have a F1 car, all right? And we want to perform the aerodynamic analysis on the F1 car. So my first question is, what should be the speed at which I run this analysis, right? So the F1 car travels from, what's the top speed of the F1 car? Can anyone tell me? A ballpark range. How fast can a F1 car travel? Right? 370 kilometers per hour. It goes from 0 to 370. At what speed does it make sense for me to do the aerodynamic analysis? That would be my first question. That's a very simple question, right? Think about it. At what speed does it make sense for me to do an aerodynamic analysis? And again, you don't have to know about F1 car at all. Just think about this from an engineering point of view. Average speeds, top speeds, okay? 250 plus, right? But instead of just talking about the speed, what are some factors that determine the speed? A car is not always going to travel at 250 miles per hour. So how do I pick exactly, Nikhil? That's what I'm looking for. It depends on the track layout, right? Now, obviously, there are certain tracks where you have where you basically have where it's easy to reach top speeds, and there are tracks where you have to take a lot of turns. Now, then comes the important question. Well, let us say that we have a track. Again, I don't watch a lot of F1 car races. I just know about aerodynamic analysis, right? So I apologize if I draw a track that looks too dumb, right? Say that we have a track like this. Again, I'm looking at it from the top view, And then say that we have another car which basically looks like your jalebi, right? Again, I know that this is totally not realistic, but let us say track 1 is there and track 2 is there. What aerodynamic performance is desired in track 1? Any guesses? If you are a chief aerodynamic engineer for a team, exactly, that minimal drag force. Aditya, why is that? Long straights, so low downforce. Well, low downforce is desired, right? You don't really care about downforce. And in this case, the only thing that you're looking for is lower drag. So that is what you need to optimize for, meaning every component in your car needs to be set up in such a way that you have low downforce. But how about this guy? Second one, exactly, higher downforce for better cornering speeds. So now, based on just the simple schematic, right? If I take track number 1, what would be the speed at which I perform the aerodynamic analysis at? For track number 1, say that you have to do an aerodynamic simulation. At what speed do you have to do it? What speed makes sense? Right. So this is definitely, I'm not going to be talking about range here, but this is definitely a scenario where we look at high speeds, right? Definitely high speeds. So what about the second scenario? We're going to be looking at low speeds, and depending upon the average speed at which a car makes a turn, you can think of that speed and you can basically do the aerodynamic analysis. But what other factors are there? So here in this particular case, you definitely are looking at the low speed range, right? But what about other factors? What other factors are there? Temperature, sure. Okay. I'm talking about quantities that you can understand quite easily, right? So from a simulation point of view, yes, in one scenario, there is high speed. In another scenario, there is low speed, correct? So what other quantities that you need so that you can set up your simulation correctly? That is what we are interested in. Temperature, tires, correct. All right. That's actually a valid point. Wind speed, exactly. In which case, wind speed might be a factor, Sohan. In which case, no, in which case is it case number 1 or case number 2? When do you have to consider wind speed to do something more realistic? Would it be case 1 or case 2? It would be the case 2, exactly, because in case 2 you see, wind speed is definitely lower, right? Wind speed is always going to be lower than the speed at which the F1 car travels. But only in case number 2, your speeds are actually low that your wind speed might affect your aerodynamic performance. But again, you don't have to consider it. But if you have to do something, if you have to do your simulation accurately, that is a factor or input that you need to consider. Because if your wind speed is say 10 kilometer per hour, just an example, and you're traveling at 300 kilometer per hour, it doesn't make sense to include wind speed. But if you're making a turn at 60 and your wind speed is 10, does it make a difference? Well, you don't know. That is why you run simulations, and that is why you test it out, right? So first of all, we kind of know that, okay, what should be, how big should we, what is the velocity of the air? That I can determine based upon the test that based upon the condition for which based upon the condition for which I'm trying to optimize the settings. The second question is, how big should your model be? When I talk about model here, I'm talking about your car. When you're loading your car into your computer, when you're loading the computational geometry, how big should the model be? Should it be a 1:1 model? Should it be should it be a scaled model, like with a scaling factor of 2? Divyam, 1:10, 1:7, Sohan scaled, okay? Based on your computing capability. Okay, that was actually a trick question. Scaling does not help at all at the end of the day. You can scale it. Exactly, it wouldn't matter. Exactly, that's why I said it's a trick question. You don't have to scale your model at all. Why? Can anyone tell me? What are the benefits of scaling a model? Like, how is it going to help me from a computational point of view? Any guesses? Or any thought? It won't, right? Why, Sohan? Why will it not help me? Number of elements depends on the size of the domain. Anirudh, okay, all right. Sohan, because the dimensions would not affect the forces. You're right, Sohan, but Anirudh is making an excellent point. The number of elements depends on the size of the domain, right? So why would it not make a difference? Why can't you scale it down? Right, so this is one of the classical things that I hear from aerodynamic students or people who are interested in aerodynamics is, hey, my computer is really, really small in terms of capacity. Can't I just scale down the model, right? It seems like a great idea, because you would think that when you scale down the model, you are still using the same mesh. And hence, when you scale down, the mesh that you use could be adequate, more than adequate for a smaller model, right? That's the thought process, which seems intuitive, but the mistake is the mesh is no longer valid. When you make the car smaller, remember, you need to have at least the same Reynolds number, right? So if you scale your car by a factor of 10, what should happen to the velocity? Can anyone tell me? What should happen to the velocity? When you scale down the size of your car by a factor of 10, how should you scale up or scale down your velocity? Or do you even have to scale it? Again, guys, would really appreciate, it doesn't change. Aditya, scale down the velocity by 10 times. Okay. Rahul says it doesn't change. Jayant, increase. Exactly. So remember, this is where simple fluid dynamics comes to your help. What is the formula for Reynolds number? Can anyone tell me? What is the formula for Reynolds number? Okay, so it's nothing but rho Vd by mu, right? So here D is basically your characteristic dimension and V is your velocity, correct? So your dimension, characteristic dimension could be, say, the length of your car, and if your length of your car, when you scale it perfectly on all directions equally, and when you scale it by a factor of 10, when you reduce it by a factor of 10, your velocity should automatically increase by a factor of 10, right? And only then you will get the same Reynolds number. Now remember, for a higher velocity, the mesh requirements would also get lower. So even though you scale down, you need to have smaller meshes so that you're resolving the turbulence. Because at the end of the day, remember, to get the aerodynamic performance correct, you need to simulate your turbulence correctly. If you're not simulating the turbulence correctly, then that's it. Your simulation results are wrong. That's it. There's no argument. So how big should your model be? What is the answer to that? It doesn't matter. So let's just pick 1:1. Just make sure that you're modeling things as realistic as you can. The second question is, how big should your wind tunnel be? Does anyone have any answers for this? How big should your wind tunnel be? So for example, say that I'll try to draw an F1 car. F1 car looks something like this, right? I apologize for the bad drawing. So, but F1 car in the side view might look something like this. And then I can basically put a wind tunnel, correct? Now my question is, what is the size of this box? How big should this box be? Jennifer says 3 times the length of the car in the front and 5 times the length of the car behind. Does anyone else have any other ideas? Sunijraj, based 5 times based on the F1 car. Okay, so that's why I'm asking, like, what is it? Rupak, it should not interfere with the boundary condition. Exactly, that's exactly correct. But which boundary are you talking about, Rupak? Are you talking about the inflow boundary or the outflow boundary? So Aditya, boundary here refers to this guy. Things that we are putting inside this circle, right? That is what you call as a boundary. The laminar flow of wind towards the car. Okay. Interesting. In the front need not be long, but the exit length needs to be long, right? So how are you making these claims, right? So again, you can see that many people are giving different answers, right? Which means there's, in general, there is no accepted idea. Like, hey, among students at least, like what should be the size of the box? Well, it turns out there is an exact way to do it. Oftentimes, remember, wind tunnel tests are done, right? People actually do wind tunnel tests. So the best way to go about that is, especially for your upstream region, right? Remember, your flow initially is going to have a uniform velocity profile. That's how wind tunnels are created. And then what's going to happen is, the wind tunnel has physical walls, top and bottom, right? So what's going to happen is there is going to be a boundary layer that gets developed in the bottom of the wind tunnel, obviously. So one of the things that people want you to validate is your boundary layer development should match with what is reported in the experiments. So if experimental data is available, you just make sure that you follow that for the inflow length, meaning the upstream length. This is called as the upstream length. So if experimental data is available, make sure that you follow that. As far as your outflow is concerned, it's not 5, it's at least 10 times the length. Why is that? Why is 10 times seems really excessive? So if your car is like 2 meters long, 20 meters on the downstream, that seems like such a big domain. Why do people do this? Well, and what is the factor? Well, it depends on the size of your wake. So what is a wake region? Wake basically refers to the low pressure region where once flow separates, you'll have really low pressure. And because of this low pressure, you will have flow recirculation. So the idea is very simple. When pressure becomes low, usually the flow here is taking place only in this direction, correct? But when pressure becomes low in the wake region, flow comes like this. And then because of this, there is a vacuum. So basically flow is kind of getting pulled into the vacuum and you start getting a recirculation region. And this recirculation region is also going to move, making the process very dynamic. So if I basically set up my fluid boundary conditions, so let me just use a different color. If I put my boundary condition exactly in this location, what's going to happen is the solver is going to get confused because a boundary condition, if you remember from differential equations, I'll just type a very simple differential equation. dy by dt is equal to e power t. So how do you solve this? You just say integral of dy is nothing but integral of e power t dt, right? Now, when you integrate this, I'll get y is equal to e power t plus c. How do I solve for c? Well, that is where boundary condition comes. When t is equal to 0, y is equal to 0, something like this, right? You give some conditions. These are called as your boundary conditions. Now remember, in CFD, you're solving PDEs. So in PDEs, you have a boundary condition here in this area and also in this area. You need to provide that, and the boundary condition needs to be a constant for a given time step, which means what you are basically saying that here the pressure is the same. In this blue line, you're saying that the pressure is the same. However, when a wake region is present, the pressure is not the same. So that is why you take this blue boundary, you put it at a very far distance so that in that location, your velocity vectors are still parallel. So on what factor does this, like how did I come up with this number 10? Well, that is purely from experience. So for example, you can take a passenger car. For a passenger car, maybe it could just be 5 times the length. If you take a truck, maybe that is 7 or 8 times the length. right? So as a factor of safety, what you can do is you can just say that if my downstream region is 10 times the length of the car, I can be certain that there will not be a backflow and my boundary condition value will be met correctly. Okay, so this is how you choose the size of your wind tunnel. On a scale of 1 to 10, please rate your understanding of this concept. I just want to make sure that this is clear before I move on. On a scale of 1 to 10, please rate your understanding. Sohan, why isn't it open then? What do you mean by why isn't it open? Sohan, can you just explain, please? Aditya, if you have a question, you can ask me. Sohan, I didn't understand what your comment was, so maybe try putting it in a longer sentence. All right. So the next question that we're going to be talking about is, what results do you need? Now, can anyone tell me, when you run an aerodynamic simulation, what results do you need? Let me answer Sohan's question. So no boundary defined, low pressure area instead of a boundary. But Sohan, the whole idea behind doing the CFD is to determine how low the pressure gets. Remember, on the back side of the car, the pressure is lower, okay? So it's called PL. And the front side of the car, you have your stagnation pressure, correct? So this PS minus PL is ultimately going to be your pressure drag, which is what you which is what you're trying to determine. So without doing CFD, you do not know what this PL is. So there's no way for you to guess that. Yes, but the backflow wouldn't then affect. I didn't understand. I hope you understand what I hope you understood what I'm saying, right, Sohan? Okay, cool. So what are some of the results that you need? Well, obviously, when you're designing a F1 car, right, you're looking at downforce values, you're looking at drag, and you're also looking at lift, right? These are the quantities that you need to predict correctly. And at the end of the day, they all depend on only two variables, your pressure and shear stress. So when you are solving the Navier-Stokes equations in CFD, it will calculate the pressure and velocity. Now your velocity gradient is going to determine your shear stress, and pressure is just computed from your continuity equation. Your velocity components should be in such a way that when you calculate a pressure, your pressure should be calculated in such a way that the velocity that you get should satisfy the continuity equation. This is called as pressure velocity coupling. This is a term that you might have seen in say ANSYS Fluent or any other software, right? So you need to be getting those results correctly. And from that, you can calculate your drag coefficient and lift coefficient. Now remember, drag and lift coefficients are normalized. They are unitless quantities. But at the end of the day, they're coming from your fundamental quantities of pressure and shear stress. So just remember that. Finally, I think this is where many people get stuck. How do you know if your results are correct? What can I do for this? So for example, say that you have a geometry of a passenger car, right? Like a Maruti Swift. And I'm asking you to determine the drag coefficient. How will you know if the answers that you're getting is correct or not? Convergence monitor can be used. No, that's wrong. Convergence monitor basically tells you if your solution has converged. There is no way for a CFD solver to know if it has converged to a right value or a wrong value. And that's a classical mistake. I'm glad that you answered it. I'm not picking on you, but that is what many people tell me. Just because convergence is reached doesn't mean that your answers are right. It just means that you are getting a solution. It is not the solution. To get the solution, as Rupak and Jennifer have pointed out, you need to go through the process of validation. So how do you do that? Jennifer, I think I've already told you the answer when we discussed about this topic before. So maybe Rupak or someone else can answer this question. How can I go about validating? Comparing it with previous results. Well, what if previous results are not available? So what do you do then? How do you know if your results are right or not? For example, every team that basically does FSAE or Baha or Supra, right? They don't do internal test, but they all do CFD simulations. How can they be sure that the results are right? They can use sensors and do what, Aditya? How will sensors help you? Rupak, any practical result, what does that mean? Right? So again, this is another place where many students are in general confused. And the answer here is very, very simple. You need to do validation, that's correct. But you need to, let me just comment on Aditya's. Use sensors to measure drag values. That's not that easy. Your experiment should be extremely controlled, right? You need to travel exactly at the same speed. The wind speed should not affect. You will have uncertainty. Your pressure sensor data needs to be calibrated. All those things needs to be done, which is why people use a wind tunnel where everything can be controlled. Because all these sensors are also sensitive to temperature variation. By using controlled box in the software, not really, no. So let me explain this in a very simple way. If you are just using your software, you cannot validate your data. The only way you can do validation is, you have a wind tunnel, and the only way you can validate or get data for your exact car is using a wind tunnel, or as Jennifer is saying, you can use track testing, but then you need, again, a lot of money to do it. You need onboard diagnostics equipment which can actually measure this quantity, right? So what if you're an average engineering college student who has none of this? Well, go through the process of validation. Now, you have websites like NASA, and there are documented databases like ERCOFTAC. I'll just write that on the screen so that people can look at this. ECROFTAC. ERCOFTAC. So ERCOFTAC is an online database that contains a lot of CFD simulations for which experimental data is provided, and also simulations from popular research groups are also available. Now, what you can do is you can find an experiment, or you can find a paper where they're doing aerodynamic analysis. And you need to kind of see, okay, if the Reynolds number is matching, then that's a great starting point. They're doing aero analysis. The Reynolds number is also matching, which means you look at what is you then take that experimental data and you try to run the computer simulations for it. Okay, I hope you guys are following. And then once you get the results from your computer simulation, you have experimental data to compare against. Now, obviously, you are not going to get the results in one attempt. You will get the results only after 15 or 30 or 20 attempts. Especially when you're a beginner, you need more attempts. But finally, you will get the right answer. Take the settings that you used, like the mesh settings, the turbulence model settings that you used, apply it to your F1 car model, your FSAE or Baja models, and then use it. Only then you can be sure that your CFD simulations is the right simulation, or else you're just performing CFD simulations for the sake of it. On a scale of 1 to 10, please rate your understanding on this topic, like how to perform validation. All right, perfect. That's what I want to see. So remember, next time when someone is giving you, when you have a object on which you have to do CFD analysis, always try to validate on a different system for which data already exists. What actual validation is? That's a great question. So what you can do is, so for example, if you take an airfoil, right? There's a parameter called angle of attack, which basically says how the airfoil is tilted. And say that you have the lift coefficient. The lift coefficient is going to increase, and then after some time, it's going to stall, right? This is a very classic behavior, fundamentals of aerodynamics. Now, for some airfoils, experiments have been done, and this curve has been obtained realistically, meaning from pressure sensors and all the things that you guys are talking about. So what you can do is, say that this blue line with the stars is your experimental data, right? You have a plot for this. Then what you can do is you can run your CFD simulation, and your CFD simulation should also predict something like this, right? If your CFD simulation is able to do something like this, then you know that you can trust your CFD solver. But then the question is, what is the allowed error? Well, especially for flow simulations for pressure coefficient, before the stall, especially before the stall. In this region, you're looking at less than a 5% error. If your lift coefficient is off more than 5%, then you're doing something wrong. Because lift coefficient is basically pressure, which can be determined very, very easily. So if you're having a huge amount of error in lift coefficient, especially when there is no stall, that means you have done a bad job of setting up your simulation. All right. Now, from an aerodynamics point of view, like what are the types of data that you can obtain using a CFD simulation? So this is like a 2009 car model. I think I just got this picture from internet. It's a very interesting picture, but this is the level of data that CFD can give you if you do it correctly. So for example, these are some of the parts, right? You have the front wing assembly, you have your front wheel suspension, you have your chassis body work, and so on. All these parts are given a color. On the left-hand side, you have two plots. You have a downforce part, a downforce plot, and a drag force plot. Now, what you're doing is, for each component, right, you're basically providing a chart of the downforce, and you're coloring the plot by the color of the part. So basically, this light brown color, right, that is for your front wing assembly, which is right here. So this is a very nice looking plot. You can actually do this in CFD simulations. So here you can see that your front wing basically produces roughly, 30% of your downforce. And your front wing is responsible for, say, 20% of your drag. Looks like there's a comment. And let us take a different component here, right? So take your front wheels. Your front wheels actually don't produce downforce. Sometimes they actually produce, in fact, they almost always produce a little bit of lift. That is what you're seeing here. But they are enormous sources for drag, which is what you see. And if you take a look at your floor and your diffuser, which is this part right here, they generate huge amounts of downforce, which is pretty well known, 50% or more. But the drag on those things is really less. It's what, say 15%. And this is where the concept of aerodynamics efficiency comes, which means, say that you want to create downforce. Whenever you're creating downforce, you're obviously going to increase your drag. But you need to design your components in such a way that the increase in drag is not a lot. So these are the types of quantities that you can basically calculate while doing a CFD simulation. And Jennifer, exactly, you're exactly correct. Depending on the track setup, these will change for sure, right? Again, if you're getting this data on track, obviously you need a lot of money to basically measure data like this. With CFD, you don't need a lot. You just need a powerful computer, and that's it. Angles can also be adjusted, obviously, definitely. As far as calculating downforce and drag, I'm not going to be going over the definition. I think maybe for the next lecture on the same topic, I can show you some formulas. But how do you get this breakdown of forces? Well, in CFD, what you can do is, once you run the simulation, you can do something called as post-processing, meaning once you get the pressure data, you can say, okay, what is the pressure force or what is the drag force just on my front wing assembly? What is the pressure or drag force just on my diffuser component? I can query that data. That is the power of CFD, right? So this is done using post-processing stage, which is basically once you've completed your entire CFD setup and you've also finished running the simulation. All right, so let me just close this guy. How much computing power do you need? I think this is one thing that I kind of put together because so many of you, when they show, like I get a lot of students. Basically, we offer courses on aerodynamics. So students come to me and say that, hey, I have this result. Does it look correct? Even without looking at the results, I sometimes say that the results are wrong. Why? Because to run these simulations, in order to do justice to these simulations, you need a little bit of computing power. What do I mean by little bit? Well, you need to have at least 6 to 12 cores and have at least 64 GB of RAM. Even this part is okay. Decent graphics card, you can live without it. But this is like the minimum requirements that you need. And why is that? Well, that is the focus of our next slide. I'll basically look at these questions first, and then I'll basically go to the previous slide. So the first thing is, I told you that you need huge computers, right? I still haven't told you the reasons why you need it. But before we discover those reasons, let me ask a simple question, or let me ask a set of simple questions. Which flow quantities should be predicted correctly for accurate results? Can anyone tell me? If I have to get my drag forces accurately and my lift forces accurately, what are the quantities that I need to predict correctly? Mass flow rate? No, that's not correct. See, one thing that you will always get correctly is mass flow rate. That is why those type of simulations can always be done on your laptops. Pressure and velocity, exactly. So Rupak, when you're talking about velocity, are you talking about just one value for velocity, or are you talking about the entire velocity distribution? The entire, exactly right. And for simplification, we can basically split the flow regime whenever there's an external aerodynamics. So for example, say that you have a small car like this, you can basically split that into two regions, right? So all the aerodynamic activities that happen, they actually happen inside boundary layers, correct? Inside boundary layers and outside the boundary layers. So these are the two regions that you can think of that exist in your problem. It doesn't matter what is the system. So there's the boundary layer component, and there is the outside boundary layer, the component, right? And then there's something called as free stream, where the velocity is just following a boundary condition. It is not at all affected by your object, correct? Even in your wind tunnel, really far away from the car, you're not going to be affected. But as you get closer to the car, you're going to get affected by the shape of the car, right? That is exactly what aerodynamics is. So when you're talking about the boundary layer, inside the boundary layer, well, turns out inside the boundary layer, it can be split into two regions, and you can do it. You can prove this from a theoretical framework. You can do some experiments and also determine it. There is a layer called as the viscous sublayer, and then there is an outer layer. In the viscous sublayer, your flow often tends to be laminar, and outside, your flow tends to start becoming turbulent. Now, if you have to capture quantities correctly, if you want to capture your velocity, if you want to capture the velocity profile correctly, then you need more computational mesh. If you don't have those computational mesh, then what's going to happen is your shear stress is going to be wrong. And if your shear stress is wrong, your drag coefficient prediction will be absolutely wrong, right? So that is where another question comes. Well, how much mesh do you need? How can I determine this? Any ideas? How much mesh refinement do you need? Mesh independence test, sure, okay, all right. But I'm asking, like, what is, Jennifer? Yes, that is the type of answer that I'm looking for. Fine mesh with layers, yes, that's correct. But Jennifer, what would you say? What would you say is a fine mesh? How would you quantify it? Inflation? No, that's wrong. 5.5 million cells? No, that's also not correct. Just because a computational mesh has 5.5 million cells, it doesn't mean that it's always accurate, right? So you guys are just talking about features. So Aditya and Anirudh, right? You guys are just talking about the features, meaning in order to capture aerodynamic quantities correctly, you need to have a fine mesh and you need to have prism layer cells. The question that I'm trying to ask is, what should this fine mesh be? Fine around component. Again, Jennifer, you're not getting the idea. But what does fine mean? How will you quantify it? When I'm asking you to quantify something, it's like this. How fast does a F1 car travel? And you said 370 kilometers, right? That is quantification. If someone asks me how fast F1 car travels, and if I say, well, it travels very fast, then that's qualitatively correct, but that's not helping me at all. Anirudh, 1 mm. Yes, that might be considered as fine mesh in certain cases, but for aerodynamic simulations, that is really, really large. 1 mm is really, really large. So the thing that you guys need to focus on is how do you quantify this? And there is a parameter called as your y plus. Okay. Yes. Well, based on the law of the wall, sure, why not? Right? So there's a concept called as y plus, which basically says how big should your first mesh be? Like, for example, say that you have your car like this, your car surface. And when I create my mesh like this, right, the first cell center should be placed at a particular position, right? This is a distance, but you can non-dimensionalize this distance based upon flow quantities, and you can calculate something called as y plus. So when y plus is less than 10, right? When your y plus is less than 10, you are in the viscous sublayer, right? Approximately, which means you can calculate those quantities accurately. And when your y plus becomes, I think, above 30, I believe, you are actually in the outer region, right? So the first question is, well, to calculate turbulence, you need a turbulence model, right? And this is where you have your K epsilon, K omega, and all that stuff. Now, ideally, if you use K epsilon turbulence model, then what you need to do is you need to make sure that your y plus value is in accordance with what K epsilon suggests, right? If the statement is not clear, let me just put it in a simple way. K epsilon model is what you call as a high Reynolds number model, okay? So say that you refine your computational mesh so that your y plus is 1, which means your computational mesh is really, really small. How small? For a Reynolds number of 200,000 or something like that, your computational mesh is going to be around 30 microns. Very similar to what Rupak is saying. Again, if you're able to get that mesh, 30 microns is really, really small. That means your y plus is 1 or sometimes less than 1, which is very good. But the problem is when y plus is less than 1 or when y plus is equal to 1, where are we? We are still in the viscous subregion where the flow is laminar. When the flow is laminar, you cannot use a high Reynolds number turbulence model. So Jennifer, I hope you I hope this makes sense to you, right? So when you're using K epsilon model, it's a high Reynolds number model. So your y plus needs to be within a range of 30 and 100. And the reason why I commented that your simulations were wrong, because your y plus was 9,000, right? So if you have to get your y plus to 30 or 35, 60, right? Say 90, say that your y plus should be 90. Your current y plus is what? 9,000. So you have to refine your mesh by approximately a factor of 100, right? Which means there is no way you'll be able to run the simulation on your laptop, right? So I hope that makes sense. So that is the quantity that you need to focus on, guys. If you did not understand anything, here's the important takeaway. Always ask what your y plus is, and always ask if your y plus is compatible with your turbulence model. That's it. These are the two questions that you need to ask at a bare minimum. In addition to this, there are more details. For example, if you take K epsilon turbulence model, which is very popular. Why is it popular among students? Well, in most softwares, that is the first model available. So people just leave it. So when you're using K epsilon, depending upon the implementation, it might not be able to handle adverse pressure gradient, meaning whenever flow separates, that turbulence model is no longer valid. It does not have the right terms in the equation to solve it, right? So these are the things that you need to question. You don't have to be an expert in the field. You just have to ask what your y plus is. You need to ask if that y plus is compatible with the turbulence model that you're using. And you need to make sure that your turbulence model is suited for aerodynamic analysis. That's it. You ask these 3 questions and then find a large enough computer. The results that you will get will definitely be accurate. So when to stop mesh refinement? This is where I was telling you about the law of the wall model or basically your y plus value. Your y plus value needs to be within a certain range, which means even if you refine your mesh too much, it's wrong. Even if your mesh is too big, that's wrong. There is a sweet spot value. That sweet spot is determined based upon the turbulence model you're using. So make sure that you stop your mesh refinement once you're inside the sweet spot. What turbulence model should you use? No brainer. You don't have to research this again. K omega SST, which is a lower Reynolds number turbulence model. Just from the name, you know that it's right. When your y plus is less than 1, you can use it. It will give you excellent results. That is like an industry standard model. Second is Pala-Talamas, another industry standard model. There are some drawbacks in both these models, which I'll be talking about maybe in an advanced lecture if people are interested. So on a scale of 1 to 10, please rate your understanding of the answers that I provided to the questions that I'm showing on screen. Meaning, you understand how you need to go about mesh refinement, meaning how much mesh you need. You understand how to calculate that. Second thing is, you know that there's a parameter called y plus, and you need to compare it against the turbulence model that you're using. And finally, there is sometimes a sweet spot in meshing, meaning you should not go too refined or you should not go too coarse. That is a sweet spot. And some practical turbulence models that you can use for external aerodynamics is Pala-Talamas and K omega SST. If you kind of understood the answers that I provided to these questions, let me know, rate your understanding on a scale of 1 to 10. In the meantime, I'll just answer the questions in the chat box. Nikhil, why would excessive refinement result in wrong results? So like I said, Nikhil, when you're refining too much, right? And say that you have K epsilon turbulence model. This is what you call as a high Reynolds number turbulence model, which means this is applicable only in flows that are 100% turbulent. But in external aerodynamics situations, near the wall, the flow is laminar. It's always laminar. So when you refine the mesh extremely, right, you basically get inside the boundary layer. Your mesh is so small that you're resolving the boundary layer. But when you're resolving the boundary layer, you're still solving the K and epsilon equations, which are part of the turbulence model. And solving those equations are wrong because they will give you incorrect values for the shear stress, which will just give you incorrect value for drag coefficient. So Nikhil, did you understand my explanation? What is the y plus parameter? Ankit, at this point, like I said, I would have to point you to a very, any standard textbook on fluid dynamics will have this parameter. So just don't refer to a local book. Refer to something like, refer to a gas dynamics book or a computational fluid dynamics book or a CFD book like Frank M. White. It might have the definition for this. Or the easy thing to do is read Wikipedia, but sometimes that can get confusing. All right, y plus, yes, so that's one. Looks like most of you have understood. Some people have not understood, I think. So I'll just let that pass. Okay. So let me basically show you how aerodynamic setup can be done. So for example, this is like a F1 wing geometry with cool looking end plates that I picked up from GrabCAD. Right, so you can see that the model seems to be split because it was actually attached to the entire F1 car. So I just split the model from it. So here the model is completely triangulated, meaning the entire geometry is represented as triangles. So this is not the mesh, okay? So what I did is I put it in a simple virtual wind tunnel, right? So the virtual wind tunnel looks like a box. If you ask me, is this box correct? No, it's not. The reason why it's not correct is I'm just showing you how to set it up, right? It's just a demonstration. So you create a box like this. You need inflow and outflow, right? So these are what you call as boundaries. So boundaries are nothing but faces in your model through which the flow will come in and exit out. As the flow comes in, it's going to interact with the component that you have placed. And what else can you do? Then you basically go through the case setup. And I'm going to be talking about only the most important parameters. So typically when you run, you have the option of running a steady state or transient. For external aerodynamics, go with steady state. That is going to give you the results the fastest time possible. Transient is required if your geometry is extremely complex and you are getting convergence issues and you don't know what to do about it. Then go for a transient solver. How far do you run the simulation? Well, one of the things that people look at is the residuals, but I say don't do that. Look at your drag coefficient value or your lift coefficient value. They need to reach a converged value. Till it reaches convergence, run the simulation. Then you have boundary conditions. The exact boundary conditions, I think we need to discuss that in a slightly advanced lecture. But for now, what we're basically going to do is, I'm going to say that my wing is a wall model, is a wall geometry, and my outside box, that's also modeled as a wall. Ideally, what I would do is I would basically do set it up as a slip wall, okay? So that the velocity there, so that there is no shear stress getting developed in those regions. At the inflow, what I'm doing is I'm providing a total pressure boundary condition. And for velocity, I'm providing a Neumann boundary condition, meaning the derivative of velocity is 0. What I can do is I can say that my pressure is 0 gradient, and I can specify a Dirichlet condition for my velocity. I can specify mass, I can specify the XYZ components of velocity. I can specify a mass flow rate. The other two options are not applicable in this case. So which boundary condition to choose? Well, the answer is very simple. You know the speed at which your car is traveling, right? That is the speed at which air should enter. So what you can do is you can provide a velocity boundary condition. And if you zoom into this model, right? And if I just hide this, you can see that velocity needs to go through minus x, right? If the velocity is going in minus x direction, it's going to interact with wing. So what I need to do is I need to basically, in this case, I can say that my x component of velocity is minus 55 meter per second. The 55 meter per second is just a guess. How would you do it? You take the speed at which the car is traveling, which is usually in kilometer per hour, and you convert that into meter per second. Looks like there's a comment. Sir, why aren't you operating the wing in ground effect? Like I said, this is just a made up simulation, right? I can do whatever I want. So since I'm just demonstrating the setup of a general external flow case, I'm not worrying about ground effect. In fact, what I'm doing here is I'm just treating this entire box as slip wall, meaning the fluid is not going to stick to the wall at all, right? Which is a very huge approximation. But the whole idea is, since I don't have wing data, right? I don't have any data in this case because I picked this geometry from GraphCAD. This much should do. I should not spend a lot of time researching and basically figuring out how I should set up the model for ground effects, especially if this is the first time I'm doing it, because I don't have any data to compare against, right? I hope that makes sense, Jennifer. Then comes turbulence modeling. Okay, see, for turbulence modeling, what is the model that I'm using? RNG K epsilon. Why? Even in this, people use standard K epsilon, and I'm using RNG K epsilon. Is this correct? What do you guys think? Based on whatever I mentioned in the workshop, what do you think? Should I be using RNG K epsilon? No. All right. What about others? So I have one no. How about others? What do you guys feel? No, doesn't depend on Y plus. Like I said, K epsilon is a high Reynolds number model, right? And it does not have terms for taking into account adverse pressure gradient, which will always occur in external flows. So in this case, it's better to use K omega SST, right? I can use this, but remember with K omega SST, my grid needs to be highly refined. I need to get up to Y plus of 1, or if I'm using automatic wall function, that is where I have a benefit. In K omega SST, it has something called as automatic wall function, meaning even if your mesh is too refined, it's not a problem, right? Because the model is a lower Reynolds number turbulence. It's a lower Reynolds number model, so it can handle that. And it has automatic wall functions, meaning if your mesh is too coarse, it would basically use the law of the wall model. Again, if you don't understand what the law of the model is, for this particular workshop, you kind of have to just accept what I'm saying. Basically, it is like you giving the answer. It's a correlation with which you are basically telling what the answer for velocity should be, or you're telling what the velocity, you are telling what is the answer for shear stress. You're providing in the answer. CFD is not doing it. So what when you use automatic wall functions, what is happening in the backend is in cells that are actually outside the boundary layer, it would solve the CFD equations. And for the cell that is actually closest to the wall, it would apply the boundary condition based upon the y plus value. If it is inside the viscous sublayer, or if it's inside the outer region, it will apply the right boundary condition. That is what you call as automatic wall function. And you will also see K epsilon with the same automatic wall function. But remember, K epsilon with automatic wall function gets rid of the y plus value problem, but it still has the problem of not capturing adverse pressure gradient. Meaning, if there is flow reversal, it's not going to do a good job. So let me close this. And then after that, you have your base grid and fixed embedding. In this case, I'm using a Cartesian mesh, which is great for accuracy, but for aerodynamics, it's generally not that much preferred in the industry, right? Because in industry, you need to create, for these type of situations, you need to have at least 25 to 30 million cells. For that, Cartesian meshes are not very, very efficient. They're very, very accurate, but they're not very efficient, right? So for that, people use like tetrahedral meshes along with prism layers to create body fitted meshes. So in this case, I'm just going to go with Cartesian mesh because this is just for pure demonstration. And then once I run the simulation, right, this is kind of the results. Again, I set this up literally 20 minutes before the presentation started. So if we still have some results, I'm looking at ParaView here. So what I've done is, just like they would do in realistic wind tunnels, I'm basically injecting some parts, some tracers on one side of the end plate. So just a second, guys. And like a couple of features you can see that you observe in real F1 cars are getting captured. You can see that how vorticity is generated here, and the flow actually turns so that it directly does not interact with the wheels. So one of the things is in F1 cars that people care about is your tires that are right behind. If your air is just going through the tires, it's facing it right away. That's very bad aerodynamics because your tires are not aerodynamically efficient bodies. So your end plate, one of the jobs of your end plate is to also make sure that there's some amount of deviation. It creates a deviation in the airflow so that your tires are not directly facing the air, right? Again, the reason why we are seeing that a little bit, but in order to see that completely, you need to model the entire F1 car, which is something that we plan on doing anyway. Now, when you see this, I'm coloring this by velocity magnitude. You can see that it's very, very choppy. The reason why this happens is because the mesh quality is very, very poor. Like I said, since I had to run it in 20 minutes, I just used a coarse simulation. So let me see if I can enable a clip plane. So there you go. You can see that I have a clip plane, and if I enable the mesh here, you can see that the mesh is really, really coarse. So let me hide the mesh here and then color this guy by, let me see if I have pressure. And I'm just going to change my color map of the pressure really quickly. And when I do that, see one thing, like I said, pressure is something that you can get very easily. And just look at this, you have higher pressure on the top and you have low pressure on the bottom, right? So that indicates, what's the word that I'm looking for? Exactly, right, downforce. The only thing is the value of downforce that I get might be wrong, but qualitatively this result is great. So this is kind of what I had prepared for this workshop. This is like I said, an introductory level workshop. Moving forward in the same topic, we'll have parts 2 and 3 and more, where we go more detail into what type of turbulence modeling, and we also go into the detail of what a turbulence model is, like what's the origin of it and why K epsilon model has the disadvantages it has, right? So with that, I would like to conclude the workshop.